Now that we have understood what is law of equipartition of energy, how we are going to apply it for monatomic, diatomic, and then triatomic, polyatomic gases basically. First, we'll start with monatomic. All right. Now, for monoatomic gases, we know that we have 3 degrees of freedom, which is the x, y, and z axis. So, 3 degrees of freedom are there. That too, it is translational. Now, energy per molecule per degree of freedom, it is going to be 1 by 2 into kb into t, right? Since we have 3 degrees of freedom, the total energy is going to be 3 by 2 kb into t. So now, what we are looking at, we are looking at the U value, that is the energy value. The U value is going to be, or you can also call it as the internal energy. U value is going to be the energy into the number of particles, correct, which is the Avogadro number. And this is what we have, 3 by 2 kBT into Na, right? And this value is equal to what? 3 by 2 RT, correct? Now, what is specific heat capacity at constant volume? CV is equal to du by dt. So, what do we have? d by dt of 3 by 2 RT, which is going to give you 3 by 2 R. If CV is 3 by 2 R, then CP, that is the specific heat capacity at constant pressure, CP, we can calculate with the help of Mayer's formula, right? CP minus CV is equal to R. So, CP is going to become 5 by 2 into R. Make sense? So, gamma is given by Cp by Cv. In this case, it's going to be 5 by 2 divided by 3 by 2, or 5 by 2 R by 3 by 2 R. Basically, you'll get 5 by 3, 1.67. So, for monatomic gas, gamma is 1.67. Suppose if I do the same thing for diatomic, they have 5 degrees of freedom, right? Since they have 5 degrees of freedom, the U value is going to become 5 by 2 kBT, correct? But 5 by 2 kBT into what? Na, isn't it? So, U value is going to become 5 by 2 RT. Now, again, CV is going to become 5 by 2 R, and CP is equal to 7 by 2 R, correct? Gamma value is what? CP by CV. You'll get it as 7 by 5, which is 1.4. This is for diatomic. Alright. Now, if vibrational motion is added to it, like carbon monoxide molecule and everything, what we discussed, then CV is 7 by 2 and CP is 9 by 2R. Okay, so your gamma value is going to become 9 by 7 or 1.28. Now, what if we do the same thing for polyatomic gases or polyatomic molecules? See, for polyatomic, what we take is, suppose see you have 3 motions, correct? Translational, rotational, vibrational. Let us say that F number of vibrational motions are happening. Okay, then U value is going to become 3 plus F into T. Then U is equal to 3 plus F into RT. Alright. Now CV is going to be what? 3 plus F into R, and CP is going to become 4 plus F into R. So gamma becomes 4 plus F divided by 3 plus F. Now look at the table. You guys will understand what is the approximate value of the specific heat capacity. See, whatever we have done is for gases, right? We can also use this law of equipartition of energy for solids. Okay. Let's try to understand the specific heat capacity for solids using the same concept. Now what we'll do, we'll consider 1 gram mole of substance having Avogadro number of molecules, Na. Alright. See, when the body oscillates in one dimension, it has an energy, right? So that energy is given by 2 into half into kBT, which is basically kB into T. Alright. Now, if I do the same thing in 3 dimension, then the energy per atom is going to be 3 times kB into T, right? Because in 1D it's kBT, in 3D it's going to be 3 times kB into T. So total energy is what? U is equal to 3 kB into T into Na, which is basically 3 RT, correct? Now what do we have? Delta Q is equal to delta U plus P into delta V, correct? Since delta V is negligible, we can say that delta Q is equal to delta U. Make sense? So what do we have then? C is equal to delta Q divided by delta T. which is equal to delta U by delta T, which is 3R. Okay. Now, this is approximate true for almost everything except carbon, which you guys will see in this particular table now. It's pretty much the same except for carbon if you look at it. Alright. So, this is the specific heat capacity for solids. Now, what if we do the same thing for water, since water is very special? Okay. So, the specific heat for water, if we are trying to calculate using this law of equipartition of energy, then what we have is U is equal to 3 into 3 kb into T into Na. Now, let's try to understand why we are getting this formula. Now, water has how many atoms? One molecule of water has 3 atoms, correct? 2 hydrogen, 1 oxygen. Since they have 3 atoms, and since it's in 3 dimension, that 3 kb into T is for 3 dimension. The initial 3 is for 3 atoms. So 3 into 3 kBT into Na. Na is the total number of molecules. What do you get? 9RT. Correct? C is equal to what? Delta Q by delta T or delta U by delta T, which is 9R. Now, what is 9 into R? 9 into 8.31, which is 74.7. You can take approximately 75 joule per mole per Kelvin. This is the specific heat capacity of water. Okay, so in this video, what did we do for gases? Monatomic, diatomic, polyatomic, correct? And we did for solids and we did for water. All right. Now you understand how this law of equipartition of energy is important to understand the specific heat capacity of any substance you want. All right.